morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's Battery Tech webinar, Power of Versatility, Polyurethanes and Electronics, sponsored by Epic Resins and broadcast by Informa. I'm Michael Krieger. I'll be your moderator today. We have just a few announcements before we begin. This webinar is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about today's speaker, download resources, share this webinar, and participate in the Q&A session that takes place at the end of our presentation. The slides will advance automatically throughout the event, and toward the end of our webinar, we will ask you to complete our survey. Please take a minute to fill this out before leaving us today, as your feedback will provide us with valuable information on how we can improve future events. And lastly, if you're experiencing any technical problems, please click the Help widget found at the bottom of your screen or type your issue into the Q&A area, and we will be glad to offer one-on-one assistance. Now, on to the presentation, Power of Versatility, Polyurethanes and Electronics. Discussing today's topic is Joe Stoller, Senior Research and Design Chemist at Epic Resins. To learn more about our speaker, please visit the speaker's widget. Joe, over to you.
Welcome, and thank you for joining us. My name is Joe Stoller. I am a Senior Research and Development Chemist at Epic Resins in Palmyra, Wisconsin. Today, we will discuss the versatility of polyurethanes for power electronics. These polymers can be modified and tailored to suit a multitude of demanding properties required in many different electric applications. To start, I will share a little about Epic Resins. Epic is a formulator of high-performance epoxy and polyurethane thermoset polymer solutions. We have been developing and manufacturing polymer solutions across many industries for over 65 years. Our R&D lab and manufacturing is in Palmyra, Wisconsin, conveniently located between Chicago and Milwaukee. We manufacture over 3,000 products and service 1,500 domestic and international customers from this location. Epic Resins is ISO 9001 and 14001 certified, as well as OSHA Sharp certified. When working with Epic Resins, our customers gain access to our technical sales team, as well as our research and development chemists. Access to our development chemists and lab capabilities acts as an extension to your design team. This level of project support helps you achieve results in condensed time frames to shorten your time to market. Automotive electronics encompass a vast range of applications. Urethane polymers touch the flow of electrical power throughout the automotive system, starting with the on or off-board chargers, flowing to the battery, followed by the inverter to the ECM, then to the powertrain. The efficient and reliable flow of energy is essential. Each of these demanding applications needs polymers to function reliably. Peripheral control systems like sensors and light fixtures also depend on urethane technology. Whether you need a polymer with high TG and thermal resistance for a motor application, or a soft polymer with great adhesion and water resistance to protect an external sensor, the versatility of urethanes can attain and exceed these demanding properties. Urethane polymers are utilized in potting and encapsulation for all of these applications. The primary purpose of these materials is to protect sensitive electronics from their surrounding environments so that they can function efficiently and reliably. The terms potting and encapsulation are sometimes used interchangeably. However, potting refers to a process where the shell or pot filled with resin becomes a part of the finished component, and encapsulation refers to when the component and cured polymer are removed from the pot to be placed in an assembly. This is an example of a potted part, and this is an example of encapsulation. Some important criteria for automotive electronics include thermal management, flame suppression, structural assembly, improved reliability and product life, and protection from harsh environments. I will explain how urethane polymers have the versatility to satisfy this list of demanding criteria. To understand the versatility of polyurethanes, you must first understand its chemistry. We formulate polyurethanes from a molecular structure to property relationship. Ultimately, we utilize our vast knowledge of molecular building blocks to impart properties needed for your final polymer. From processing requirements for viscosity and gel time to physical properties of tensile strength, elongation, glass transition temperature, dielectric strength, and thermal conductivity, all of these properties can be adjusted to satisfy specific requirements. I will expound on each of these properties along with the formulation and testing involved for urethanes to have this versatility. We will begin with gel time. Gel time is generally defined as the time required for the reaction of the polymer to proceed to a point where the polymer has more elastic properties than fluid properties. More specifically, when a two-component material is mixed, the viscous properties dominate. As a polymer begins to react, it displays more viscoelastic properties in a dynamic nature until the polymer chain gets long enough that the elastic nature is more prominent than the viscous nature. The process for each application will have a specific demand for gel time or throughput requirements. Urethane polymers can have very fast reactivities to just a few minutes to as slow as several hours. This versatility gives your process engineering team latitude to fine-tune their process. Urethane chemistry has more reaction versatility than most polymer types. This versatility is rooted in two unique properties: the molecular structure of the monomers and the catalyst mode of action and activity. The building block molecules that can be utilized in the production of polyurethanes have different reactivities. These reactivities are dictated by their molecular structure. The position of the reactive group will change how fast it reacts. For example, this is an NCO group on an MDI, and this has a 4-position NCO group on this side, has a 2-position NCO group on this side. The 4-position is much faster. If you formulate with MDI with more 4-position NCO, you will have a faster reacting polymer. This allows us to utilize the appropriate molecular structure when tailoring the reactivity of a polyurethane. Catalysts can also be used to craft the specific reactivity that an application needs. There are catalysts utilized for slow and consistent polymerization for delicate applications requiring gradual reactivity. In contrast, some applications require very rapid polymerization for high throughput applications, as seen in this demonstration. When we combine our knowledge of molecular structure reactivity with the nuances of catalyst types, the gel time possibilities of polyurethanes are essentially endless. Different test methods are used to quantify gel time based primarily on the speed that your application needs. The first test is ASTM D3056, also known as the Sunshine Gel Meter test. This is a diagram of a Sunshine Gel Meter. This instrument works by submersing a glass rod into the mixed material and slowly turning the glass rod. When the material reacts to the point where the glass rod can no longer rotate, the upper electrodes touch and sounds an alarm. This method is primarily used for urethane systems that react very quickly for a fast transition to an elastomer. Typically, this is for systems with a gel time of 20 minutes or less. The second method is used for systems with a slower transition from a liquid to an elastomer. This method utilizes ASTM D2196, which measures viscosity in centipoise as the polymerization reaction proceeds. Ultimately, this test monitors the viscous nature as the polymerization reaction transitions the material from a liquid to an elastomer. In most cases, gel time is defined by a terminal viscosity that is prescribed based on the application where the material is being used. Typically, this method is used for systems with a gel time of 20 to 40 minutes. The third method uses a rheometer to determine when the elastic properties of the polymer dominate. A rheometer is an instrument that simultaneously measures both the flow and deformation of materials. During the curing process of a urethane polymer, these fluid and elastic properties are dynamic, making a rheometer key to the characterization of the curing polymer. More specifically, we look to analyze two properties as the thermoset cures: the storage modulus and loss modulus. The loss modulus is a measure of the fluid properties of the material, versus the storage modulus is a measure of the elastic properties of the material. In this graph, you will see the quantitative analysis of the loss and storage modulus of a curing thermoset. As the two-component thermoset begins to react, you can see that both the loss and storage modulus increase. They will both continue to increase until they reach what we call the crossover point. At this point, the elastic properties overtake the fluid properties. We relate this to the no-flow point in the reaction, which is analogous to the gel time. Additionally, the rheometer can precisely measure this crossover point at any temperature between -40°C and 100°C. This type of analysis gives your process engineer vital data for manufacturing improvements and optimization. Once the polymer is gelled and completely cured, we turn our attention to the cured properties of the polymer. Glass transition temperature, or TG, is an important thermal property with great versatility in urethanes. TG is the temperature where a material transitions from a hard and rigid glass-type material to a soft, pliable material, as shown with the vertical blue strip on this graphic. Each application within power electronics has varying operating temperature ranges, resulting in different optimum TGs. Typically, applications with sensitive components and vibrational conditions will find greater longevity with a low TG product. For example, motor controllers or battery management systems contain sensitive electronics that can be damaged from thermal cycling in under-the-hood environments. Utilizing a soft, low TG urethane elastomer will protect these components from these thermal and vibrational stresses. Alternatively, motor applications that run at high temperatures for prolonged periods need a material with high thermal stability, requiring a high TG. A high TG polymer gives greater molecular stability and polymer longevity, protecting motor conductors from harsh environmental conditions. The TG of a system is primarily influenced by the molecular linkages and frequency of these linkages. These linkages are classified by three different architectural features of the molecular building blocks: the backbone structure of the monomer, the molecular weight of the monomer, and the functionality of the molecular structure. All three of these architectural features come together to influence the cross-link density and hence the TG. These features influence the TG because as the polymer heats up, the linkages begin to flex, stretch, and move. The density and type of these linkages dictate the temperature at which this occurs. Therefore, by manipulating the backbone structure, the molecular weight and functionality of that structure, we manipulate the TG to fit the desired application specifications. This animation demonstrates how two polymers can have different cross-link densities and hence TGs. We measure TG on a thermomechanical analyzer, also called a TMA. The TMA functions by using a quartz probe to measure the height of a small polymer sample over a temperature range. This is the graphic result of a TMA. At the low temperature portion of this graph on the left, you see the pre-TG CTE from -40 to 0 degrees C of 61 part per million. As the temperature increases to the right, you see an inflection point on the graph at about 60 C. This is the TG. Below this temperature, the polymer is considered a rigid polymer, and above this temperature, the polymer is a soft, pliable polymer. To the right of the TG, you see the post-TG CTE. measured between 75 and 106 degrees C of 170 part per million. The post-TG-CTE is typically higher than the pre-TG-CTE. It is important to understand where the TG of the polymer is relative to the application operating temperature range to reduce component stresses that occur in this thermal transition. Additionally, the rheometer can be utilized to measure TG. We analyze this by conducting a temperature sweep of a cured polymer. In this example, we cure a polymer between the parallel plates. Once cured, we ramp the temperature from low to high in the same manner as the TMA, but instead, we measure the storage modulus over this temperature range. As you see in the graph, the storage modulus is very high at low temperature. This indicates it is a rigid polymer. You will notice that the modulus drops precipitously, showing the transition from a hard polymer to a soft, pliable polymer. This occurs at the same temperature as the TMA analysis, which shows the relationship between TG and storage modulus. Another critical property of your polymer is physical strength. Physical strength is a measure of a polymer's ability to withstand deformation. There are a myriad of methods to evaluate physical strength, but the most common is to evaluate elongation and tensile strength of the cured polymer. These two methods give us a good snapshot of how a material behaves under stresses, allowing us to get a clear comparison to other polymer systems. As you can see in this chart, polyurethanes have a large range of tensile strength and elongation. For example, urethanes can have soft, gel-like properties similar to a silicone, or be formulated to be hard and rigid like nylon or polycarbonate. You notice each time we look at how to modify a urethane property, we look at its chemistry. Similar to how we modify the TG, we again look at the same molecular building blocks: the backbone structure of the monomer, the molecular weight of the monomer, and the functionality of the molecular structure. When looking at the tensile strength and elongation, we put a little more emphasis on the backbone structure linkages. These backbone structure linkages and their frequency are great tools to modify the strength of the polymer. I like to use the analogy that these backbone structures are a little bit like springs of the polymer. The type of linkage in the backbone combined with the cross-link density will result in different tensile and elongation properties. For example, I have two different springs in my hand, a rigid spring and a flexible spring. The rigid spring is like the conjugated hexane ring in a molecular backbone, which tend to be more rigid. This flexible spring is more like the polyethylene glycol linkages of a hydrocarbon, which are more flexible. If you have more conjugated hexane rings in the backbone, it will be more rigid. If you have more polyethylene glycol linkages, you will have more flexibility. By knowing how these molecular structures affect the strength of the polymer, you can then understand how to formulate the polymer with strength like polycarbonate or a softer polymer similar to silicone. To measure tensile strength and elongation, we use the Instron Universal Testing Instrument. A specimen is made with a specific measured test section, commonly called a dog bone, and a constant pulling force is placed in the specimen. As you can see in this video, the sample is pulled until failure. At failure, the maximum force is measured in pounds per square inch or pascals. The test method used is ASTM D412 or D638. D412 is designed for soft, flexible elastomers, and D638 is for hard, rigid materials. The main difference between these two tests are the shape of the dog bones and the speed the sample is run. Typically, D412 is run at 0.2 to 20 inches per minute. This allows for materials with higher elongations to be tested. D638 is run at 0.1 inches per minute, which is required for hard, rigid materials with lower elongation. Thermal management is critical for most electrical applications, making thermal conduction crucial. Thermal conductivity is the measure of a material's ability to conduct heat. This infrared video gives you a visual representation of three polymers with different thermal conductivity. These three products are EPIC 7524, RM 2018, and S7527. S7524 on the bottom left has low thermal conductivity. RM 2018 on the bottom right has medium thermal conductivity. S7527 on the top has high thermal conductivity. The infrared image shows as the pucks are heated from the bottom, you can see that the S7527 gets hot faster than the other two, indicated by the yellow color. Obviously, this shows it is pulling heat from the hot plate faster than the S7524 and the RM 2018. Applications that process electrical energy can produce large amounts of heat. Dissipating this heat is vital to performance and longevity. Polyurethanes have great versatility to provide thermal conductivity for potting and encapsulation applications. Choosing the correct thermal potting compound for your power electronics will improve efficiency and lifespan due to reduced thermal cycling from better heat transfer. This graph compares the thermal conductivity range of common materials. Polyurethane systems can have thermal conductivity from 0.2 to 4 watt per meter Kelvin, with the same range as silicone materials and much higher than acrylic or nylon. Polyurethanes can be formulated to provide the thermal transfer required for some of the most demanding applications in power electronics. Refining the particle kinetics of the potting compound is key to improving its thermal conductivity. The thermal conductivity of a polymer is primarily dictated by the type, size, and loading of a thermally conductive mineral filler in the polymer. When formulating for thermal conductivity, the first decision revolves around filler type. Different mineral fillers have varying thermal conductivity as well as other properties that are imparted into the polymer. For example, aluminum oxide has excellent thermal conductivity and is very hard. Aluminum trihydrate is lower in thermal conductivity and not as hard, but has flame suppression properties. Once the mineral is chosen, the thermal conductivity can be further optimized based on the level of loading and the size of the particles used. To illustrate this, I have three different sets of marbles. This first picture shows a lot of large marbles with lots of interstitial space. This second picture shows smaller marbles, but still a significant amount of interstitial space. This last group of marbles is a mixture of many sizes. You can see much better contact of the marbles. The marble example demonstrates how particle size distribution helps optimize particle contact and loading to improve overall particle kinetics and thermal conductivity. Heat transfer and thermal conductivity are measured using a modified transient plane source method. This is a diagram of how the method works. A known current is applied to the sensor's spiral heating element, providing a small amount of heat. A guard ring surrounds the sensor coil to support a one-dimensional heat transfer into the sample. The applied current results in a rise in temperature at the interface between the sensor and the sample. The rate of increase in the sensor voltage is used to determine the thermal properties of the sample. The voltage is factory calibrated to temperature. The thermal conductivity is inversely proportional to the rate of increase in the temperature at the point of contact between the sensor and the sample. This measurement only takes 1 to 2 minutes. This allows for rapid test turnaround time. Large data sets or multiple samples can be evaluated in a short time frame. Next, we look at the viscosity of a polyurethane system. Viscosity is the measure of the force of deformation or resistance to the flow of a liquid. For comparison, this graph shows the viscosities of everyday materials compared to polyurethane systems, which range from 200 to 10,000 centipoise. For potting and encapsulation, the flow of the urethane is essential to protecting sensitive components from a myriad of environments. Without proper flow, these components will not be sufficiently coated and thus not protected. This video is a great example of flow in and around sensitive components. You see the potting compound being injected under the PCB. This produces complete underflow of the board in addition to flowing up the vent holes and completely around the board components. When developing a manufacturing process, viscosity data is vital to achieve complete encapsulation of components. Many factors affect how a urethane potting compound flow in an application. The primary factors include monomer molecular weight and its functional groups, the level and type of filler loading, and the use of wetting agents. In most cases, the cured properties will primarily dictate the monomers used, so viscosity typically must be adjusted through the modification of fillers and wetting agents. When mineral fillers are used in a system, their particle size has a significant effect on the viscosity of the system. Ultimately, with smaller sized particles, there is a greater surface area to interact with the resin monomer. This increases the viscosity. As the particle size of a filler increases, the surface area is lower, which in turn reduces the viscosity. This graph shows how particle size affects viscosity. The material with a smaller particle size filler has a higher viscosity, and the opposite is true for the large particle size with a lower viscosity. Wetting agents are another tool that can help to reduce the viscosity of systems with high filler loading and/or small particles. Wetting agents work by interacting with the filler particles in place of the resin, changing the viscous interaction and reducing viscosity. For example, this video shows two identical polyurethane systems with and without wetting agent. The material on the left contains a wetting agent and flows much better than the material on the right, which does not contain any wetting agent. When adjusting the viscosity of a system, these tools allow for vast adjustment to reach an application's requirements. The viscosity of materials can be measured in many ways. The most common method is ASTM D2196, also known as the Brookfield RVF viscosity. A Brookfield RVF viscometer measures the viscosity of materials from 10 centipoise to at least 1 million centipoise. This large range allows for precisely categorizing the flow of a material for an application. To further enhance the precision of viscosity measurements, different surface area spindles are used depending on the viscosity. For example, spindle 7 has a very slow surface area for high viscosity materials, and spindle 1 has a much higher surface area for low viscosity materials. The last property we will discuss is dielectric strength. Power electronics are evolving into sophisticated systems with intricate electronic components and high voltage systems in smaller and smaller packages. Ensuring that these components remain isolated from each other in these condensed architectures is essential to preventing electrical failures, fires, and potential hazards. This is where polyurethane potting materials with high dielectric strength come into play. When an electric field surpasses a material's dielectric strength, it undergoes dielectric breakdown. This breakdown can lead to electrical arcing, short circuits, and damage to surrounding components. For EV electronics, safety and reliability are paramount. Minimizing the risk of dielectric breakdown is a primary concern. Urethane insulating materials are essential to EV electronics to prevent dielectric breakdown due to their inherent high dielectric strength. Selecting the right material with the appropriate properties is crucial. To improve dielectric strength, you need to understand the mode of failure in dielectric breakdown. The factors that influence dielectric breakdown of a polymer include polymer type, filler type, and loading, as well as any additives present. Dielectric breakdown occurs when the molecular stability of an insulating material allows electrons a free path to travel. Ultimately, this is about stability of electrons in the material. This is an illustration of dielectric breakdown. As a voltage is applied, electrons build up on the surface of the electrode. If there is a path of unstable electrons, the charge will travel through the polymer as shown. The more stable the electrons are, the more difficult it is to make them move through the material. We formulate polyurethanes that have molecular structures, fillers, and additives with very stable electron shells. When formulated this way, it significantly impedes the flow of electrons and increases dielectric strength. To test the dielectric strength, we utilize ASTM D149. This test is conducted by placing a test sample between two electrodes, a cathode and an anode, surrounded by a dielectric oil bath. We then increase the voltage between the cathode and the anode until an arc passes through the sample, or the voltage between the cathode and the anode reach 50,000 volts. Dielectric strength is reported as a ratio of the voltage at failure divided by the thickness. This is reported as volts per mil. It is important to note that the thickness of a sample will change its performance. When comparing the dielectric strength of two materials, they should be tested at as close a thickness as possible. Before integrating a potting material into power electronics, thorough dielectric strength testing is essential. With the wide range of important criteria in automotive electronics, a versatile polymer is essential to satisfy these needs. Whether you need flexibility to improve your manufacturing process, or you are fine-tuning your component design to take reliability to the next level, or any combination, polyurethane chemistry can be modified to help achieve those goals. At Epic Resins, we are industry leaders in formulating innovative urethane polymers. Our R&D chemists continuously develop new materials with novel molecular structures to withstand the unique and extreme demands of EV power electronics, battery systems, sensors, and lighting. These urethane polymers have the versatility needed for your electronics application.
Now, before we begin with today's Q&A, please direct your attention to our webinar survey available next to the presentation window. If you close the survey, you can reopen the widget by clicking the icon along the bottom of your screen. And again, thanks in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. And now, on to the Q&A portion of our event. As a reminder, to participate in Q&A, just type your question into the text box located next to the presentation window, or click the Q&A icon at the bottom of your screen. If we are not able to answer all submitted questions during today's webinar, we'll be sure to share them with our speaker who can reply to you offline. Here it is. Hey, let's get started with a question from Charles, who asks, is Epic Resins focused mostly on potting materials? And do you offer materials available for molding?
Thanks, Charles. Thanks for the question. So no, we actually do both potting compounds and encapsulation materials. Again, it really depends on what the customer needs. You know, if they need something that's going to have more of an encapsulant that's going to act as, you know, that protective coating with no shell, then, you know, obviously the polymers and the type of structure that we build is going to be based upon that, and obviously vice versa, a material that's for a potting compound. So,
okay, thanks for that. Here's one from Lloyd, who says, I have a TG reported as run on DSC. Is this equivalent to your test, and is one test better than another?
Oh, that's a good question. So yeah, so I didn't really talk about it in the presentation because we really do report TG from TMA, but DSC, a differential scanning calorimeter, measures the heat flow of a sample, and you'll see a change in the heat flow during the TG, and so you can define that in that test. And I guess the short answer to the question is yes, they're very, very comparable. The nice thing about TMA, and the reason we use TMA, is the TMA also gives us CTE, so the coefficient of thermal expansion. And that property is really important, especially in PCBs that have obviously mostly surface mount devices. So those are pretty sensitive. So when you have, the coefficient of thermal expansion changing, it's really important to have that data point as well. But and that's why we report that. Whereas DSC doesn't give you that data. It'll give you good TG data, but not necessarily CTE.
Okay, great. Thanks for that. This one from Nella, who says, can a material be both thermally conductive and have flame retardant properties?
Yes. I don't know if the slide was up for very long, but lots of different filler materials can be used in an application. So I'm going to use the one I had in the presentation, the ATH. That is also used as a flame retardant, but because it's a mineral filler as well, it does have some some thermally conductive properties to it. So it's the balance between how much thermal conductivity you need and what flame suppression you might need will kind of give you the balance between how much thermal conductivity you get and flame retardant.
Okay, great. Keep the questions coming. This one from Katerina, who asks, what are the main challenges of working with urethanes in these applications?
Sure. So probably the biggest thing, the most important thing to realize is that urethanes are moisture sensitive. I use the analogy, we're making urethane elastomers. The same chemistry is used to make urethane foams. When urethane materials are contaminated with water, atmospheric water, which is all around us all the time, that'll start to react and produce some. Want to make sure that, and it's really easy, either dry nitrogen or drying cartridges on your dispense equipment. It's pretty easy to mitigate the moisture, and it depends on the environment that you're in too. Most of our customers are either using dry nitrogen or a desiccant dryer for the inlet on their system.
Okay, great. Keep them coming. This one from Eric, who says, in EV, what scenarios PU potting will be used?
Oh gosh, lots of them. So big one is motor controllers, battery chargers, battery systems themselves. A lot of battery manufacturers want polyurethane as an insulating material, as a flame retardant material, for the thermal conductivity materials of that battery pack. So, anywhere really where you need to protect components from an outside environment, urethanes are really, really great choices.
Okay, great. Raphael says, great presentation. I'd like to know if an epoxy pretreatment on the polyurethane load, like graphite, could keep it anchored to the PU matrix.
Potentially, yeah. So the important thing is that you want to make sure that you're going to be able to react those two interfaces. So, whatever you're coating with epoxy, you need to make sure that the functionality that you end up with on the outside of that is going to be able to react with the urethane. So in most cases with epoxies, if you're using an aromatic, an amine of some kind, it could be aromatic, it could be aliphatic, lots of different types of amines. But if you have some extra amine groups, those amine groups will react with the isocyanate group. So it's important to make sure that you have some of that functionality. And in the end, you'll have to run the test to see how it works. But I would expect that to work, actually, yeah. Okay,
great. This one from Nella, who says, what kind of performance testing can you do?
Oh gosh. Probably the most useful performance, and when I say performance, I'm talking about performance in someone's part, right? We have lots of different tests that we can run on the polymer itself, but to really look at the performance in the part is our thermal chamber. So we can run for very low temperature down to -40 C upwards of 100C. We can also do humidity along with that, and then that can set up as we can set that up as a cycling process. So that's one of the most demanding tests that you're going to see in a lot of applications. Where moisture is involved, thermal cycling is involved. And if it can survive that type of an environment over many cycles and many hours, normally that's a really, really great life test to give you a good understanding of how it's going to survive in the real world.
Okay, great. This one from Thomas, who says some circuits are sensitive to static electricity. Is that ever a problem during potting, and are there PU properties that minimize the possibility?
So in my experience, no, I have never had a customer that has had a problem with that. In my experience, normally they're very careful about static dissipation of the line as well as of operators on the line. And as far as the urethane material causing an issue, that I have never seen that. So.
Okay, good to know. This one from MJ, who says, how do epoxy and urethane compounds compare in cured properties?
Sure. So generally speaking, epoxies are going to be more rigid. They have generally more cross-link density, more of those backbone structures that generally give a polymer more of a rigid at room temperature. And then hence they're also, because of that, going to have a higher TG as well. Whereas urethanes are going to be generally softer. We can attain lower TGs, a little bit more flexibility as well with urethane systems versus epoxies. Urethanes generally have a little bit larger range, so we can hit some of the higher hardnesses with urethanes that epoxies have, but we can't always hit the lower hardnesses with epoxies that urethane systems have.
Okay, this one from Nella, again, who wants to know, how is hardness related to TG or tensile strength?
Sure. So remember that the TG, and I guess the important thing to think about is glass transition temperature is what TG stands for. So you can imagine something that's glass is really rigid, so it's going to be really hard, right? So anything that when your material is below its TG, it's going to be hard like a glass. It's going to be really, really rigid. And then as you get above the TG, right, it's no longer a glassy material, it's a flexible rubbery material. So that is going to be a softer material, okay? And then when you compare that to your tensile strength, you're generally of rigid materials, you're going to have a higher tensile strength. Because it takes a lot more energy to deform a rigid material than it does a softer material. So in the example of being below the TG, a rigid material, you're going to have a higher tensile strength and a lower elongation. When you get to that softer, pliable region of that polymer, it's going to have a lower tensile strength, but much more elongation, ultimately.
Okay. And here's a question from Joseph, who says, heating resins help with the viscosity for flow, but does it also shorten the gel time of the resin?
Oh, absolutely. Yeah. Good. Great question. Yeah, absolutely. So the manufacturers in many cases that use our materials will want to try to reduce that viscosity even a little bit more. Generally, we kind of give the recommendation that for every 10 degrees C increase in temperature, your gel time is going to get cut in half. So let's say at room temperature, you have a material that has a 30-minute gel time. At room temperature, I'll say 25C. If you go to 35C, instead of a 30-minute gel time, you're going to be at 15 minutes. So it's really important to realize. And a lot of customers also, what really works well is to preheat the part, because you get an instantaneous heating of the material. It hits that part like you saw in the video, it immediately flows out, and it's happening at a much faster rate than as it's getting heated first, coming through the mix tube, and it's starting to build viscosity in the mix tube. So again, it comes down to the manufacturing process design, but either thing can be used. It does shorten your work time.
And here's one from Eric, who asks, what's the thermal resistance limit for PU?
Oh gosh, so it really it's going to depend on that backbone structure again. We can formulate urethanes that are going to have really great thermal resistance. And you're talking about, for example, like RTI testing. We have some urethane systems that have RTIs of greater than 140C. So we can formulate anywhere in between. There really wouldn't say that there's necessarily a limit. We have a really huge range that we can really formulate a product to suit those needs.
Okay, great. Raphael wants to know if there's an application which can be used even PU and silicon, which of them is better to be used?
It really, again, it comes down to the customer's requirements. What I will say is, in many cases where silicones are used, urethanes can be used as well. A lot of times it comes down to what the first product was that was tested or whatever. But and urethanes are generally a lot more cost effective. We can get some really great properties out of a urethane at a significantly lower cost than silicones.
And with that, that's all the questions we have time for today. Thank you. We appreciate your time and expertise on today's topic show. And thanks to our sponsor, Epic Resins, as well as to everyone in the audience. We appreciate your attention and participation. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your peers and colleagues who may have not been able to join us live today. Finally, this webinar is copyright 2024 by Informa. The presentation materials are owned by or copyrighted by Informa Markets, and the individual speaker is solely responsible for their content and opinions. On behalf of our guest, Joe Staller, I'm Michael Krieger. Thanks for your time, and have a great day.